Okay, we will start the last session of the day before going for the panel discussion. So our next speaker is Eduardo Santos from Tree Drivers. He will give a speech on the sustainability and life cycle analysis of the START project. So I hope you enjoy these last talks. Eduardo.
Thank you very much. Good afternoon, everyone. Back again. Okay, so we will start this presentation on the sustainability, environmental sustainability, and also economic sustainability. Just to begin, because this is the final meeting, Tree Drivers, we are a research and consultancy firm. We have more than 20 years existence, and so we are very much specialized in this type of environmental and economic analysis. And so I would like, of course, to thank my fellow colleagues, and Giovanni is one of them that is here today, and also my other colleagues that could not be able to be here today. But they have been very important throughout the project and the work, and so I would like to thank them. And so, to begin with, this was the fundamental question that we were challenged to answer. So could or can start tetrahedrite thermoelectrical devices be sustainable from the economical point of view and also from the environmental point of view? And so this was the main challenge that we had to answer. Oh, sorry, just skip one slide. So the main objective, as Tree Drivers, we were involved in the task 5.3 as part of the work package 5 on the device production, evaluation, and demonstration. And so we were focused on the life cycle assessment and the life cycle cost analysis. And the objective of our work was mainly to assess the relative economical and environmental performance of the tetrahedrite-based thermoelectrical device, and also the comparison of this with the same performance of commercially available devices, so that we can assess whether this could be a potential sustainable technology. So as we have today widely addressed in many of the presentations, this is the concept behind the START project. Not necessary, of course, to remind this, but for us it's just important to recall that life cycle assessment and the life cycle cost analysis were heavily depending on the information and data that was coming from the development of the other project stages. So, of course, it was a process where we were analyzing the performance of the environmental impacts and the costs and revenues based on developments that were done on the prototypes and the materials and the processes for manufacturing that were developed throughout the project. So the task really accompanied the development of these work packages. And so also the challenge was, as part of the project, not only to assess the sustainability of the technology that was developed, but try as much as possible to assist during the development of these work packages with sort of guidelines and hints on whether the decisions that were being taken for the materials and the processes and the technologies, the components, were sort of going in the right direction in terms of sustainability. So we tried to do that. But ultimately, what we had to answer was that question about whether the end technology was sustainable. And so in order to do that, we applied life cycle assessment and life cycle cost analysis methodologies. This very much incorporated the definition, of course, of goal and scope for the methodology, for the analysis, sorry. we had to define a functional unit, so it's very much important as part of this environmental and also economic analysis to establish the functional unit so we can compare the performance of the technology within the applicable unit, and also to be able to measure these against other competing or commercially available alternatives in the same unit. Then, of course, one of the most hardworking and challenging phases, which was doing the inventory of the processes, consumptions, emissions, materials, and also, of course, the inventory of the costs and revenues that are incorporated in each of the life cycle stages. And then, of course, we achieved or obtained the results and made the comparisons and then bring the final conclusions. As part of the development, of course, this work also inputted with the dissemination and communication for work package 7, with the development of scientific articles and communications, and also as part of the of work package 7, exploitation. So we tried to develop, of course, data sets for the processes. We had to do this for the environmental impact and the cost analysis. And now, at the end of the project, is one of the outcomes is that we have a database with many of these processes characterized and that we can use for future analysis. And also, with this database, sort of try to provide either services or some sort of commercial viability, commercial product, which we can use to basically allow other technologies to be assessed as well. And so going on to a bit more details on the scientific or technical methodology that we use to do the life cycle impact assessment. So of course we use the help of softwares, and in this case CIMAPRO software, and also databases that are already commercially available, which sort of speed a lot the process of developing the life cycle assessment. But of course we had to improve this, and we had to use, of course, data and information that was provided throughout the project by the partners in order to build on with new processes and new information categories that were then inputted into the methodology. I would just outline that the scope of the life cycle assessment was cradle to gate initially. So we didn't focus at the end of life because this is such a new technology that it's really hard to determine or assume which could be the end of life processes, how this eventually can be recycled. But we also ended up also doing some assumptions and analysis based on scenarios where we also considered the end of life phase. We defined the functional unit to provide the output power based on 1 kilowatt hour input, using, of course, the tetrahedrite device that was developed within the project. And of course, the life cycle inventory, as I said, was the most hard working or the biggest challenge, and was done with data coming from the partners and from literature, of course. And just going very quickly through the scientific methodology. So basically, what we did was to calculate what is identified here as midpoint impact categories. So using the life cycle impact assessment method, we calculated the impacts in each of these categories. So it's a lot of categories, but it's very a wide range of categories that allows us to characterize many of the impacts of the complete life cycle. And these have the specificity of having physical units. So it's what characterizes these midpoint impact categories and these midpoint analysis, is that each of these categories has specific physical units that you can measure and sort of assess. But we didn't stay there. So Many of these are sort of too technical and are good to be included, of course, in this context of the project to do a technical analysis. But we also wanted to do more like subjective analysis based on the sensitivity of the impacts for the humans in particular and for ecosystems. So we also had in consideration the endpoint indicator, where we would have in consideration what is called the damage pathways, which is basically the subjective validation or ponderation of the quantitative indicators. And so this is, we use reference methods, so we didn't do any research specifically to quantify the subjectiveness of these indicators. So we use the standard methods. But just to say that when we are moving from midpoint indicators to endpoint indicators, we are adding subjectivity, and so the interpretation gets a bit more like qualitative rather than quantitative. But both of these indicators allows us to have a sort of full view on what the sustainability level of the project and the technology are. So the system itself, it's no novelty, of course, for everyone in the room, and for sure we and I in particular are probably the least qualified person here to talk about in the room about this. But we had to take this in consideration to sort of break down the composition and the processes that are used to produce and manufacture such technology. And so, based on information from our partners, we were able to create material composition for these models. So it's a model of the materials and a model of the assembly. We also, in this model, considered the stages and the processes used to extract the raw materials, to generate the materials themselves, to put those materials together and do the assembly and to do the parts, and to put them all together in what is a thermoelectrical device. Of course, with the characteristics of the using tetrahedrite as a material for specific components, the P-type leg, of course, but also all of the other materials that are used to complete the whole device itself. So it's not only, of course, the tetrahedrite material that is used. So we used, of course, a lot of the information from our partners and also a lot of it from the literature to reinforce those informations and those validations. Throughout the process, as I told initially, we tried as much as possible to bring the results throughout the different stages of development of the technology in the project. And so, of course, as it has been translated here, initially there was an idea of using as much as possible 100% natural tetrahedrite coming from the mine waste. That eventually proved not feasible. And so this also provided an opportunity for our modeling to see how the evolution of this composition could also translate into either improvements in terms of sustainability or not necessarily as improvements. So we started off as 100% tetrahedrite use of natural tetrahedrite, and eventually ended up with a mixture of tetrahedrite from natural sources and from synthetic material. In terms of environmental impact, I showed earlier a list of an extensive list of categories. So there is a lot of them on the standard method, but we just focused the analysis on 4 of the main ones, which are there: global warming potential, human carcinogenic toxicity, mineral resource scarcity, and also fossil fuel resource scarcity, which were sort of outlined as the most indicative in this case, because they represent the majority of the impacts, but also they are good indicators of what we are looking for in terms of comparison with alternative commercial viable components compared to the tetrahedrite-based one. So these were the selected indicators, and those are the ones which we will be focusing on in terms of results. And so here we have the first set of results for the environmental impacts. And what we can see on the left-hand side, of course, is the sort of relative position of the start tetrahedrite-based thermoelectrical device, which is there signaled as a start. And we compare these with the results that are that we sort of modeled for in some cases. Other cases are based on literature for different technologies. And overall, what we can see in these four impact categories, which as I said, we selected because are the most representative, is that the start tetrahedrite-based thermoelectrical device is one of the lowest impacts among the different technologies that are already available, either commercially or at least referred to as existing with according with the literature. So as we can see, START has the potential to have very low environmental impacts. Very much one of the best ones and placed in many of the categories, as we can see, maybe in terms of global warming potential. So it's one of the lowest impact categories. Compare, for instance, with bismuth telluride, which is one of the leading commercial competitors. And this we have analyzed and has very much to do with the fact that with raw material extraction for bismuth, you require a lot of material extraction and processing in order to achieve the same volume of material that you would require to get the tetrahedrite. So this is one advantage where tetrahedrite is sort of more concentrated in this case for the START project than the bismuth material. Of course, this is highly beneficial in terms of impacts and is also a direct consequence that we are using mine tailings. So this was one of the initial drivers from the project using mine tailings, and the results are showing here as being beneficial. Other examples with the mineral resource scarcity and fossil resource scarcity are very much associated with the same argument. So it's the same driving factor that you have to process a lot less material. So this brings down the impacts in terms of emissions, but also in terms of resource scarcity and also the fossil resource scarcity, in the sense that this indicator is very much associated also with the energy or the fuel consumption in this case to generate energy for the raw material extraction and also for the production processes. Human carcinogenic toxicity. So there is a lot of toxicity categories in the impact method that we used, but we focus on this one, the human carcinogenic toxicity, which is a good indicator of the health risk that these materials can take. And so we can see that the START really is a high performer in this case. And this very much comes with the fact that we are using sort of non-toxic material compared to other materials that are used for competing alternatives. And so here on the bottom right, despite all of this good news for the tetrahedrite leg, we can also see sort of a picture of where the contribution from the environmental impacts is coming from for the different categories and from the different materials and components. So what we can see is that the use of tetrahedrite P-type leg is generating a lot less impact, which is good. But at the same time, what this tells us is that we have significant impacts, for instance, for global warming and fossil resource scarcity coming from the alumina plate, which is also one very important component for the whole device, not just the leg itself or the P-type leg. And also solder paste is showing a very high contribution in terms of mineral resource scarcity. And for toxicity, we have the other N-type leg, which has the different material composition from the P-type leg. and so the materials are used there are contributing significantly for carcinogenic toxicity. So what this tells us, this result is that if we are to improve further, the tetrahedrite P-type leg also is definitely bringing the sustainability or the environmental impacts is bringing them down. So it's a heavy positive contributor. But now if we want to improve the overall environmental sustainability of the component or of the T device throughout, we have to look into other components as well. So in particular, alumina plate and the solder paste as well. And so the result previously we were showing per kilowatt of power output. If we are to consider also the power output and the area, the result further improves. So we have here, well, the relative position where we had the tetrahedrite-based component when we were considering per kilowatt hour. So this means that it can potentially have a significant high power efficiency compared also to the other competing alternatives. But if we are to consider as well the square meters, this is also a good indicator that the technology that is being developed here in this project not only is sustainable from the environmental perspective, but it's also efficient in terms of the power efficiency, but also its architecture. And it's important because, of course, I'm not the specialist person here to do this claim, but what is very clear is that if we want to improve any sustainability for this component as well, we have to make sure that the amount of power that it gets to the square meter is also very high, because heat is, well, the hot side, let's say, it's exposed, and also the cold side is exposed to a determined amount of energy per area. So we have to, as much as possible, capture all of this energy with by the area, by the surface area. So this is also an important parameter also for sustainability, but at least based on our assessment, the START technology has a very high potential for being sustainable in this aspect as well. And so now jumping on to the life cycle cost assessment results. So what we did was, as I said previously, we did the inventory of costs and revenues as well, because it's also, of course, a source of revenue that we can generate power, and we can sort of sell that power or use that power as avoided cost, not needing to acquire power and instead using the power generated by the thermoelectrical device. And so on the left-hand side, what we see is the main contributors for the costs and revenues, and of course by the life cycle stage. And of course we can see that the production and assembly essentially is the main cost bearer of the whole life cycle. And the main costs factors are the production of the heat exchanger, also the electricity that is used to power the processes for manufacturing, and also we have there the adhesive bonding layer, which is also a very costly process. So these three are sort of determining the whole life cycle cost of the technology. So we have a bit there on the raw material acquisition as well, but this is comparatively to other technologies smaller because of the particularities of the project. So we were using mine waste, which was essentially free or with some cost. But of course, this has to be taken in consideration if we are to do an expansion of this to have like a huge production. So this would sort of impact that cost over there, and potentially could increase these factors. We have considered as well the revenues coming from the use phase. they are positive, but still they are not significant when we compare to the costs of transportation, of production, and also the end of life potentially can generate revenue in the sense that if we are able to recover these materials and recycle them, and eventually there is already a circular economy for these materials so that they can be fed back again into production processes, they can potentially generate revenue from selling those secondary materials. Of course, many of these analyses, either for life cycle assessment and also for life cycle cost analysis, they have been embedded with many assumptions that I have not been discussing here extensively. But this sort of gives us a range where we can be potentially putting the sustainability of this technology out there if this is to become a standard technology. When we compare to two of the most common technologies, so bismuth telluride and lead telluride, in terms of cost balance per kilowatt for power output, so we can see that the start tetrahedrite-based component can be within the vicinity of the lead telluride and a bit even lower than the bismuth telluride. So this, I mean, these results are not fully precise in terms of absolute value. So there is a range here, and it's heavily depending on many of the assumptions. But what we can say with certain degree of certainty is that we will be within the vicinity of these cost performance of other competing technologies. So it's a good indicator that this technology can effectively perform also in economic terms. And just to finish with the results, again, if we are to have in consideration the surface area aspect, so the architecture of the component itself, of course, this is very much based, again, with the preliminary or with the results coming from the project. This would even improve a little bit. So the architecture of the start tetrahedrite-based device can also even be improved or better performance if we take in consideration the surface area. So we can take as much power from the heat exchange equivalent to other technologies. And so this brings us to our, I think, conclusions on this initial question on the sustainability, both economical and environmental of the technology that has been developed within the context of this project. So first of all, the use of secondary raw materials, in particular the tetrahedrite source from the mine tailings, is a very good inductor of low toxicity. So this was one opportunity and challenge that was an initial driver of the project. And in fact, it has been confirmed that by using this material, tetrahedrite, we comparatively to other technologies, we are lowering a lot the toxicity of the outcome component. So we are lowering the impacts in that sense. Also, it can have lower environmental impacts or in the same order of magnitude and even lower range than competing technologies for mineral and fossil resources. And also in terms of costs, it can be within the same vicinity, of course, heavily dependent on lower costs of acquisition, which have been a particularity of this project, which would have to be, of course, confirmed if it was the case of mass production of such a technology. And overall, what we can say is that at this moment, of course, very much a prototype-based technology yet, but we can say that it is already a sustainable technology. It has a very good environmental performance, and it has a prospect economical performance as well. Despite these, on top of these conclusions, we can say that there is potential and room for improvement in terms of sustainability if further development can be done, looking at those components like the aluminum plates and different components, but also on the integration of all of these materials in the same component. And so I think that was it. Thank you very much. It was a pleasure to be part of this consortium. Thank you.
Thank you very much, Eduardo. So I don't know if there is any questions. Martin, I remember in Lisbon you had some questions. All the doubts have been removed, I think, with these updates on the life cycle analysis. I don't know if you remember your question. Yeah,
It's true.
indeed.
It's not so much kilowatt, but kilowatt hour, because things are paid in kilowatt hour in the end. I saw your graph. So for me, translating that to kilowatt hours would still be useful, but I think that's beyond the scope of the project. So
Yeah, but it's a very good comment. Actually, we also, of course, did the analysis for kilowatt hour, but the thing is, we opted to show these the indicators with power output because it would be heavily depending on the assumptions of how long the thermoelectrical device would be working, how many kilowatt hour would be producing and generating. So we sort of try to avoid this, and of course, as you have all for sure been able to see, we didn't bring the absolute values for the slides itself. Of course, they are part of the deliverable, but just to see the relative position more importantly than the absolute values, because those are hard to have a sensitivity for those. So they can vary a lot depending on the functional unit that we consider, and if we consider by kilowatt or kilowatt hour, the values will be different, but the relative position will be the same. So that was the idea behind it. But for sure, the life cycle will generate kilowatt hours, and that is the money maker, let's say. Yeah, exactly.
Okay. Thank you very much. So the train of the START project is approaching its last station. But the good point is that the last station, there is an airport and you can take a flight with the START Alliance. And there, that's the legacy of the START project, where Emese from La Palma Research Center will give a talk to finish and give the last speech of today, and then we will have the panel discussion. So the floor is yours.
Thank you, Hamid.
Yeah.
So my name is Emese Karácsonyi. I'm an innovation manager working for La Palma Research Center, who was a partner responsible for exploitation and innovation of the project results. And today, at the end of this project, I will summarize START's legacy, which you will see it's about the alliance and a service company. So what we have today is that the thermoelectric ecosystem in Europe is emerging, but not yet fully connected. We are missing a fully integrated value chain in Europe. The market visibility and coordination is rather low, and the commercial pathways are not yet clear. On the other hand, what we see by the project end, and which was confirmed today, that there is a strong innovation potential with sustainable thermoelectrics. Today we were so far talking about tetrahedrite-based thermoelectrics, but we can even think about a broader future. But still, these so that we have these results of the START projects, it's just the starting points, and we would like to have a long-term market impact on after the project. So transitioning from the project, we aim to build a long-term structure, and as a starting point, what we have for that is an alliance, which we called Sustainable Thermoelectric Alliance. Then we established the company called Start European Thermoelectric Systems Ltd. And we launched a digital platform called Start Technology Marketplace. All these to support the thermoelectric value chain. So the objective is to ensure continuity, strengthen the impact, accelerate market uptake of sustainable thermoelectric technologies along the value chain. Just a few words about why we decided to establish this approach is at the beginning we were thinking about, or at least the grant agreement, we promised to have a service company by the project end, which would be making business out of the project outcomes, and the Start Technology Marketplace, which is the digital platform. So the focus is to be on exploitation and long-term continuity. While during the discussions, we realized that, of course, the technology outcome of the projects are not fully ready for commercialization. So the business opportunity is not right away there. But still, we would like to build this ecosystem along together. So we decided to have the alliance as a flexible approach for establishing the ecosystem for sustainable thermoelectrics. And this is already enlarged to, as I mentioned, not just for tetrahedrites, but for any solution which are sustainable and which has to do with thermoelectrics. And the company is to be as an operational and commercialization support for the alliance. All these are connected with the digital platform for visibility, matchmaking, and collaboration initiation. So that's the present approach. So I have a few slides about the alliance and then about the company. So the Sustainable Thermoelectric Alliance is a collaborative network for the creation and growth of the sustainable thermoelectric ecosystem in Europe. You can see the founding members. 12 members of the START consortium signed a memorandum of understanding, which is the basis for this alliance. And you can see the mission here is to represent, connect, and strengthen the ecosystem by accelerating innovation, enabling market uptake, shaping supportive policy, and fostering collaboration across industry, research, and public stakeholders. So at the end, we have a vision of a climate-neutral, technologically sovereign Europe, where thermoelectric generation and cooling are widely deployed as efficient, reliable, and sustainable solutions. So the alliance was launched formally on the 6th of March, or May, so a few weeks ago. And it is meant to be open to new members who have similar interest and expertise. Okay, so the core values, here you can see we focus on sustainability, scientific excellence, collaboration, industrial competitiveness, integrity, and transparency. And you can see we defined 6 key groups of actions. As you can see on the slide, policy and advocacy is the first one, market enablement and commercialization, research, innovation, and technology road mapping, industrial ecosystem and value chain development, communication awareness and skills, and critical raw materials mining and circular value chains. So I will go into a bit deeper in this if I should talk a lot. Yeah. So the first group is containing the policy, advocacy, and representation. So here is the objective to influence EU and national policies to support thermoelectric deployment and innovation, because if we have that, then at a point businesses can start building on it, but it is much needed that we have thermoelectrics highlighted in policy. So for that, we are planning to develop common policy positions and white papers to engage with institutions of the European Union, contribute also to standards and regulatory frameworks which are supportive for thermoelectrics, and coordinate national advocacy through members' chapters. So what I'm reading now or showing to you is the strategic plan, which is the main document coming along with the Memorandum of Understanding. The first version is set for 3 years, starting from 2026. So these are, we gathered all the actions which might be necessary. And this is quite a large pool, so we have to define where to focus on and in which priority. So the second action group is about market enablement and commercialization to reduce barriers to the adoption and increase the market pool. We plan actions adopting the publication of application-specific use cases and business cases. We already developed 2 pilot business cases during the project for the industrial partners, application-specific business cases. So we could do similar actions which would show the potentials in the thermoelectrics. Also, we aim at supporting pilot and demonstration projects, engaging end users in industry, mobility, ICT, healthcare, and any other sectors where thermoelectrics have some potentials. Also facilitate access to finance and public procurement, and develop life cycle and sustainability assessment. Then the third group is about research, innovation, and technology road mapping in order to align R&D priorities with industrial and societal needs. So actions may be adopting a European thermoelectric technology roadmap. We already did this exercise for tetrahedrites for the START project, but this could be further extended and applied for other focuses. Then another action may be fostering collaboration between academia, RTOs, and industry, and then support scale-up of materials and manufacturing processes, and promote open innovation and shared test facilities. The fourth group is about the industrial ecosystem and value chain development, with the objective to strengthen European manufacturing and supply chains. Here, adopting the mapping of the European thermoelectric value chain is potential action. Then partnerships between SMEs and large industries should be encouraged. Standardization and interoperability may be adopted and supported. And also, if we still think about the raw materials and recycling, we should be engaging with similar initiatives. You can see that for each group, we have already an initial set of key performance indicators, which we will be looking at once we start these actions. Group number 5 is about communication, awareness, and skills. Here, of course, to build recognition and human capital for the thermoelectric sector. by developing a strong European brand, adopting the organization of annual conferences and thematic workshops, engaging with media, policymakers, and the public, and support education, training, and industrial programs which are relevant. Group number 6, about critical raw materials, mining, and circular value chains. Here, we aim at positioning thermoelectric generation and cooling as a strategic downstream sector within European critical raw materials policies. So aligning the associations, the alliance's strategy with European Critical Raw Materials Act and other national strategies. Establish a structured dialogue with European mining companies, refineries, and material processors. Support any R&D which are CRM is efficient, and advocate the inclusion of thermoelectrics in CRM-related IPCI's innovation fund calls and strategic projects. And the last action is just to, as a reminder that we have the company to support the alliance, where we aim for good collaboration, and facilitate the evolution of the sustainable thermoelectric ecosystem together. Here, that's it. So, some words about how the alliance is operating. So here, members can support alliance activities on a voluntary basis through their expertise, resources, and services. Also, activities may be organized through work streams or project-specific arrangements or agreements for the future. Regarding governance, we have two main bodies, the General Assembly and the Alliance Board. The General Assembly is the main decision maker, where one representative and one vote per member organization is defined. And the Alliance Board is now set as a simple one with a president, a vice president, and a secretary. The Alliance Board is responsible for the day-to-day coordination and management of the Alliance. For now, decision-making is set also in a simple way. If we progress and evolve, we might change this, but decisions adopted by simple majority vote for now. And also, we encourage electronic voting where appropriate. Of course, we are all around Europe, and that makes it simple to organize such meetings with decision-making points. So presidency is a rotating. We established this on an annual basis. So members may be presidents unless otherwise decided. And the president coordinates activities and chairs the General Assembly with the support of the service company. The alliance remains open to new members, as I mentioned, and new members are admitted upon the approval of the General Assembly. So we, as I mentioned, that we have just been established, and the first meeting was held on the 6th of May, where we mainly focused on the formal launch of the alliance, the government structure establishment, and the board was elected. So we have the president Felipe Neves, the START coordinator, of course. We have Vice President Martin Den Heyer. So this way we have research aspects and also industry aspects represented. And myself is the secretary for the alliance. Okay, so the second meeting we are going to hold today after this workshop or final event, where we just continue what we started. So confirmation and adjustment on operational framework, and we start discussing the key actions of the plan. Okay, so some words about the company. So this was, we just accomplished the original plan as well, and also this way we have a legal entity representing the needs of the thermoelectric sustainable ecosystem. So this company is mainly to support the commercialization of sustainable tea technologies and to facilitate the development of the ecosystem. This is, as mentioned, a service-oriented entity, and it was established by the founder of the La Palma Research Center. And the mission is here to accelerate the deployment of thermoelectric technologies by supporting the activities and growth of the alliance, connecting stakeholders across the value chain, and enabling commercialization and market uptake of promising solutions in Europe. The vision is to become the leading European hub for thermoelectric innovation and commercialization. The core services here, which were defined along the project run, and so this is the final set. So we aim for digital platform services, the provision of such services through the START technology marketplace. Matchmaking and networking across the thermoelectric value chain is an important service we wish to offer. Then fundraising and proposal development support for relevant projects. Market intelligence, niche market investigation, commercial feasibility assessment. Also regulatory compliance assistance and sustainability assessment, LCA/LCC studies, mining byproducts and raw materials evaluation. Here, so as just to repeat that the company is an intermediary in establishing the thermoelectric ecosystem and supporting members, and this is it's a collaboration with the START members, START partners as well. Some slides about the technology marketplace, which is kind of an umbrella for the alliance, for the service company, and also for the START project outcomes. So we have the START website, which was functioning all along the project, but we established this technology marketplace, which is more focused on the commercial aspect and the ecosystem aspect of the project outcomes. So here the key features already, you can see a version which was freshly launched. You can see the link on the bottom of the slide. We already put some information which might be interesting for ecosystem players or potential players. So we have there the START innovation agenda and roadmap for commercialization, a few section of the outcome which was generated in the frame of work package 7 of the project. Then we have some START tools which are meant to support business feasibility studies, and we have also the serious game linked to this platform, and there are sections that aim for providing extended insight on sustainable thermoelectric technologies and markets. Okay, so here are a few print screens about the platform. So there are menu points, and Now you can see the menu point of the START technology marketplace. So here, roadmap to commercialization, and I mentioned the START Series game. So if you haven't tried the game, and please go ahead. This is a game for all ages, so your children can join you on the mobile phone as well, if you let them. Okay, so next. And the last, no, not the last slide, but I have two more slides. So on the next steps, we are planning in line with the strategic plan and in line with the business plan of the company, is launching activities in order of priority. Then welcoming new members to the alliance in case of interests, and the cooperation with similar initiatives. So we have Sustanet with overlapping partnership. Already, it's easy to start the collaboration at that point. We are in connection with the European Thermoelectric Society, and we could start discussions with them as well. Then fundraising for covering activities, it's quite important, so that we have more effort for the actions planned. Also, consideration of strategic partnership agreements for different collaborations between alliance members, and if all goes well, we can establish a legal background for the alliance at some point. So the impact and invitation. So we aim at building a European value chain for sustainable thermoelectrics. And what we meant here is energy efficiency, circular economy, sustainable materials. So these are the key aspects where we wish to talk about sustainable thermoelectrics. So I invite everyone who is interested to join the alliance and to collaborate with the company and start using the marketplace, which we plan to enlarge further. So let's build the thermoelectric ecosystem together. So thank you very much for your attention, and also for the cooperation within the START project.
Thank you, Mase. I don't know if there is any questions. No? So, yes.
Thank you, Ms. Just one stupid question. Is not the presidency for 1 year too short? Should not be 2, at least. Because the project is already, well, the project is going to finish now, and that starts 2026, 2028, and you have 1 year, so Philippe is on its way out already before even coming in.
Well, the alliance is launched now, so the year is starting now, and the memorandum of understanding says something like, of course, the president can be re-elected or remain as president, so we don't have to send him away after 1 year if he wants to stay. Yeah.
Okay, so it's time to have the panel discussion. So I invite Martin, Geoffrey to join Emese. We will have also Luis as a moderator of this session. Also, we will have 2 panelists joining us remotely. So I don't know, Bruno, you can... Yeah, we can see Doug already on the screen. I don't know if you also see us from... Yeah.
Yep.
Okay, and Dario also joined us. Maybe I will give you the microphone. You can. Mine is not working. No, you don't have to. It's control. No. One.
Dois.
Maybe the other one. Yes. Yeah, it
Oi.
should work.
Okay. This one works. So let's kickstart this last session of today. This is the round table. First of all, let me welcome everyone, both the participants that are here and online, and also the audience. We will try to have a nice discussion today in this round table. We are going to cover, of course, thermoelectrics, but our objective here is also to discuss the future and how can we jointly join forces for the Thermoelectric European Association or some joint force of some kind. Thermoelectric technologies, they are becoming relevant nowadays. We have been talking about it all day. There is growing interest in the technology, also shown by the potential applications discussed today. We mentioned waste heat recovery, but they can also be important for cooling, sensing, and autonomous power generation applications. However, as we also have been discussing through the day, there are several important questions that we need to consider due to the state of the technology. So, for example, how constrained are we by critical raw materials? Which material systems are truly scalable? How can we move from laboratory outputs into marketable products? And how do supply chains, geopolitics, and sustainability considerations influence future deployment? So there are some interesting questions to be answered. We will try to cover some of them with our panelists. They come from different backgrounds, thermoelectrics, through the thermoelectrics value chain, not only the materials or the device development, but also through sustainability. We will start here with some quick introductions of the participants, and we'll move to some questions led by me, and then we open the floor to questions from the audience before concluding this session. So first, let me start with the online experts. So Dr. Doug Crane is here joining us. Hello, Doug. So Doug Crane he works on thermoelectrics technology development and is a leading expert in the innovation and optimization of thermoelectric heat to power and thermal management. He worked previously as director thermoelectric engineering at Alphabet Energy, and also as a principal engineering of thermoelectric systems at Gentherm. So Doug has several expertise in the industry, as well as research. He has over 25 patents and patent applications, and has authored several book chapters and peer-reviewed papers in the field of thermoelectrics. He holds a bachelor's in mechanical engineering from the University of California, and a master's and PhD in mechanical engineering from the University of Maryland, where he studied the simulation of thermoelectric waste heat recovery and automotive cooling systems. So Doug is here to give us a perspective, of course, of thermoelectrics from the industry side, but also from the USA, where he comes from. We have been discussing Europe. This gives us a new perspective. So a round of applause to Doug, please. Thank you for being available. Then we have Professor Dario Narducci, which is a physical chemist, and also a professor, as I said, at the University of Milano. Specializes in solid-state chemistry and material science. He has done his PhD in Milan, and he also has conducted research at IBM. He has been working in both the research side of things, as you can see, but also he has joined startups related to thermoelectrics, so also bringing this perspective of research, industry collaboration. Since 2008, he has become a leading figure in thermoelectricity. He is the current president of the European Thermoelectric Society, and he is the secretary of the International Thermoelectric Society as well. He has more than 170 scientific publications and 18 patents, and his recent work has focused on hybrid photovoltaic thermoelectric systems and on how to advance the global understanding of thermoelectrics phenomenon. Thank you, Dario, also for being available. A round of applause, please. Now we move here to our in-person, let's call it, participants. We can start here with Mr. Geoffrey Raw. He's an electrochemical engineering with a PhD from the University of Louvain, specializing in thermoelectric materials and systems. And he has more than 15 years of experience, also connecting the research academia side of things with the industry. Where he is currently a research and development manager for Thermo Power Systems, which is a startup aiming to deploy sustainable thermoelectric generation at industrial scale. In parallel, he also works as a senior research associate at the University of Louvain, leading research across different activities ranging from new materials development to the design and characterization of pilot scale demonstrators. His profile combines deep technical expertise, hands-on industrial development, deployment, and a strong commitment to bringing sustainable thermoelectric solutions to scale. Also, round of applause to Geoffrey. Thank you for being here. Then we can move here to Emeshe. So Emeshe is an innovation manager from La Palma Research Center, as she mentioned before in her presentation. She has a master's degree in environmental management and policy, and more than 20 years of work experience in the fields of research and innovation, while she has been involved in several EU framework programs and projects. Her major work focus is on the facilitation of bringing research results into the market, helping to raise the TRL level of research outputs. Her main areas of interest include green innovation and technologies, eco-friendly solutions, circular economy, waste reduction, and clean energy systems. And this is very well aligned with the development of sustainable thermoelectrics value chains. So, round of applause to Emeshe. Thank you for also being here. Last but not least, we have Martin, also a participant in the START project. Martin has a master's in mechanical engineering at University in Delft, and a post-master study in computer-aided engineering. He has worked in several different sectors. As an engineer and project manager, he worked in food processing, pharmaceutical industry, later in the aerospace sector, where he led the development and production of Airbus aircraft components. Then in 2013, he created these two companies. So RGS, which is now called Thermagy and Imagy, companies working in power generation and power storage. And this is where also the thermoelectric side of things come here. As part of his general management role, he has led the Thermagy team during the next-gen radioscope thermoelectrics generation development phases. Thank you, Martin. Round of applause as well. And I believe now we can pass to the discussion. Again, thank you all the experts to be being here for this roundtable. Yeah, today we have been discussing the START efforts, what we have as a project been doing in different stages of the value chain, trying to create this sustainable based groundwork for the future value chain for thermoelectrics. This is, however, let's say a focused European project. So Doug, let me start with you and ask you to give us a perspective on how thermoelectrics is seen currently in the USA.
Well, I mean, I think thermoelectrics has changed considerably since I joined Gentherm over 20 years ago. For instance, Gentherm is no longer sort of focused solely on thermoelectrics and no longer has a focused R&D arm. And TE startups such as the former company I was at, Alphabet Energy and GMZ and Evident, just to name a few, have unfortunately not survived. So it is a difficult place to work. Long-standing thermoelectric companies such as Marlowe, which is now Coherent, and Laird, which is now TARC, have been bought out and have changed their focus from what they were primarily doing before. One of the things that I see too, and this relates, is that even though these are there are U.S. based thermoelectric companies, much of the mass production for U.S. companies in thermoelectrics is actually done in Asia, whether that's in China or Vietnam or Japan. Much of it is done in Asia. So that's just some of what I see. I do see that companies such as myself at DTP Thermoelectrics obviously continues in thermoelectrics. We are more focused on the thermal management and cooling side of things than power generation, but nonetheless continue to work to develop thermoelectric materials, devices, and applications.
Okay, thank you, Doug. Now let me bring back this discussion to Europe, and I would like to ask a question directed to Martin, Geoffrey, and Dario, because all of you have experience with both research and the industrial side of thermoelectrics. So I believe you have a very good scope also on the thermoelectrics value and supply chains. So I would like to ask you, can Europe build its own thermoelectrics supply and value chains? And if not, what is missing? Who wants to go first? This is a question for the three of you. I believe you can jump with different.
Following Doug's explanation of what happened, I think one of the major events in thermoelectrics was happening 15 years ago when the automotive changed to electric focus rather than combustion engines. And I think that was, before that, was the leading traction of thermoelectrics. Looking at the today's situation, I think, like in the US and Europe, we are still a bit in a puzzle, in a mix-up, where we need to go with thermoelectrics, which is mainly dominated at the moment with the market of thermal management, like Doug also indicated. So it's the cooling side, the Peltier effect instead of the Seebeck effect, and partially, but quite niche, is the application in space, like we are participating in at Germany. So in principle, I think the focus for me is not so much on on the production chain, but it's rather on the value chain. It could be that production low cost later on ends up elsewhere. I don't know. But it's for the time being, I think our search to find good solutions thermoelectrically, working solutions, which can be produced at scale and which can be produced at a certain cost level, working in certain temperature areas, and making the step to an application, to a series of applications in all kinds of ways. I think that is the major challenge at this moment, and I think that is valid in the United States and in Europe equally.
Yeah, and maybe I would add that really regarding manufacturing chain of thermoelectric modules, in Europe, I do not believe that we can reproduce what is in Asia. But we can prepare and make a new processing chain from new thermoelectric materials that are really sustainable, which is not the case of state-of-the-art thermoelectric materials. And maybe these materials will be for some new applications, some niche application, but definitely we can open new manufacturing route and new application for this manufacturing route. But reproducing what is made at low cost in Asia, here in Europe, I think it's not possible, definitely.
To add my own view, well, I think that we all agree on the fact that thermoelectricity is still by far and large a solution in search of a problem. We have no killer application. We tried to find it in thermal harvesting, but it didn't work, or at least not for now, save for the space applications. And thermal management seems to be a good opportunity at this time. So your initial question was if Europe can handle to have its own set of companies. I think that they should, because thermal management is a key issue, as a key enabling technology for a number of applications, from a data server to artificial intelligence. And if we don't have this opportunity, we don't take this opportunity to show the power of thermal electricity, we're missing a good occasion. Talking about production, I also agree that the problem with, at this time at least, with thermal electricity is that it was shown just a few minutes ago. Most of the cost of thermal electricity is manufacturing. The fact that you have the assembly, which is still by far and large artisanal. So you have a lot of labor costs, which is nothing that we can sustain in Europe or probably even in the United States. So you have to go in different countries to make them. Either we change this kind of approach, we make it automatic, we reduce the cost of labor, or Europe itself will be unable to do the real manufacturing. They can commission it to somewhere else, but it's nothing that we can handle in Europe because of the cost of labor.
Thank you for these answers. We might come back to some of these topics later on, but Emeshe, let me ask you, how do you see, based on also what the other participants have commented here about Europe and what is missing or what are the roadblocks, how do you see both these two outputs from start, the sustainable thermoelectric alliance and the SETS company? How do you see them entering this field? Can these two bodies, in some capacity, cover some of these gaps?
I was just listening the feedback on the previous question. Well, it is challenging, so that's why we have the alliance. That's why we have to start collaborating within Europe with other initiatives and try to find the focus where we should really put effort into. So now, if I think about the niche market, so if we go for applications which have a niche applications which could be could make Europe as a leader. That's an option, and yeah, I don't have a view on, like, regarding production. I think we will not be dealing with that, the alliance and the company, but services, supporting the ecosystem in any way. So we just have to listen to what industrial stakeholders find the best way to go ahead, and beside that, yeah, convincing policymakers to put focus on such markets and potential applications, or funding. That's also another way we could accelerate the process.
Okay, thank you, Emeshe, as well. You all mentioned some kind of either application or market approach. So maybe I can ask, what do you think it's the strongest? And I think some of you already addressed this kind of question one way or another in your talks. But what you believe is the strongest commercial opportunity for thermoelectrics technology? There has been research in thermoelectrics technology for a while now, like a lot of research with not much real application to show. So what do you believe are the best approaches? You mentioned thermal management, moving away from a little bit from waste heat recovery, but what do you see are the best bets for successful value chain on thermoelectrics? It's a question for everyone. So who wants to jump in? Doug.
I'll jump in to start. I mean, I think for power generation, well, for both power generation and for thermal management, you know, the key is sort of cost effectiveness for that. So, you know, you need to have high performance, and you also need to have something that where it can be manufactured and is cost effective, so that we keep the cost down. Right now, it has seemed that, you know, thermal management would seem to be closer to being able to do that in certain niche applications. I think, you know, if performance could be at a higher rate, and cost could be lower, it would potentially open up, obviously, more of these opportunities, both in power generation and in thermal management. But the opportunities are there. Dario mentioned the data center thermal management and AI. You know, that's a potentially huge opportunity, which is going to be begging for an appropriate solution. But there's obviously many more. For instance, even data centers, there has been interest, and this is not really new, but there's been interest in whether you can recover waste heat from a data center. There's certainly lots of it. It's low grade waste heat. So again, it's how can you make the thermoelectrics potentially efficient enough at those temperature levels to provide enough cost effectiveness, enough benefit that justifies the cost. So anyway, those are just some of my thoughts.
Thank you, Doug. Who wants to jump in next? Martin.
Yeah, I think don't underestimate that thermal management or cooling is a market which exists. So that is not so negative, but it's not so much the Zeebeck effect, but the Peltier effect. And indeed, those basic components are produced in Asia, but the implementation of it is done in Europe. So that is clearly, or in the United States, let's say in other parts of the world, in any application that exists. So that is okay. I think the What I've seen since I entered the thermoelectric community is there was, apart from bismuth telluride modules, which are available and scalable, and you can just buy them off the shelf, there was an incredible search for some power generation capacity at the mid-temperature range. And that problem has, in my eyes, never been completely solved. It was also one of the attempts in our project with getting beyond 200 degrees Celsius with the tetrahedrites. I think that's underway, but it's still a puzzle that has to be made. Whenever you talk about power generation from harvesting or from combined heat and power, you need to have something which can cope with the thermal environment that such a component is operating into. So I think thermal, for us, we have renamed our company to Thermergy. Why is that? Because it has so much to do with thermal engineering. Every one of these systems is in effect is thermal engineering. When I look at markets, and we have our first experience was getting into waste heat in the steel industry, and he showed some of that. That was already happening in well, almost 10 years ago. And then you have to fight against an electricity tariff of a few cents per kilowatt hour. And for me, that was quite a learning point, because that is virtually undoable. Even if you reduce the cost of these modules really significantly, that will be a challenge. And that is a matter of how the whole energy system works. And I think that we have been spoiled in a way, because everything was so cheap. The learning point I had, if you have to compete with electricity costs, it will be difficult. If you have an additional value, which is quite clear in space, there's an additional value, because you're fully remote, you need to have something which is completely reliable for a very long period of time, then there's a clear distinction of the function. I think it's the same way what Hao discussed about sensoring in remote places, that has other advantages, like reduction of installation cost or reduction of cabling cost or whatever. And if you take those kinds of things into account, then I think it stands a better chance. Apart from the thermal management aspect as such, what we see happening is the thermal management, accurate management within a very small bandwidth of temperature control in critical equipment. That is a really good function for thermoelectrics still.
Yeah, I agree that maybe the most promising application for power generation would be in the autonomous system. So either powering some sensor, but maybe some combined heat and power system for isolated area or stuff like this. Because just power generation, you will always struggle with efficiency of thermoelectrics, and you will always fight against other technology and physics that have higher efficiency, that in the mid-term, I would say, development, we cannot think to beat. So we will always lose. So we need to fight with the real strength of thermoelectrics, which are the one that why we are using them in space and other area about long-term stability, reliability, and not just efficiency. And one key point, although I agree with Martin, was this is always a problem of, it is a problem of material science, but it is also a problem of thermal engineering or engineering in general. And there exist a lot of applications where thermoelectrics already work or could work, but usually people are not trained to work with thermoelectric, and they just try it with they choose the wrong thermoelectric modules with the wrong heat exchanger, they interface them on the wrong way, and they just say, oh, it doesn't work. And this is really one missing point I see in the value chain of thermoelectrics, is there is no standard method of engineering thermoelectric system for a given application. And so it always, if you are not in the field, it's always really difficult to design a good system based on thermoelectric, because you have to deal with material science, heat exchanger, power electronics, and this is really hard to master all these discipline, I would say.
Dario, would you like to jump in on the application aspect?
Can you hear me?
Yeah.
Yeah. Okay.
Yeah.
I was just saying that I fully agree with Doug. With this is cost effectiveness is a key point for any kind of technology. This is quite obvious. The point is maybe there's something more. Of course, it's a matter of in case you want to have some kind of harvesting, thermal harvesting, how much it costs to make a watt hour, if you prefer, of energy. But it's also a matter of where you make it. At this time in Europe, we have an open call, which is a Pathfinder challenge, which is aimed at the development of micro harvesters for application wherever you cannot have wiring to bring power. So basically, sensing networks are object of this kind. And at this time, the only solution you have are batteries. Batteries that have to be replaced, while in principle, thermoelectric harvesters could be forever. So this is an additional point we should consider and making a value out of it when we compare thermoelectric generation to other ways to make power. They can be made very small. They can be suitable for micro harvesting. They are, they do not require any kind of servicing. So they're basically without any maintenance cost. And this is something that matters. This is not true for batteries, of course, where you have to make replacement. On the side of thermal management, I think that one other point that we should consider is that, at least in Europe, at this time, there is quite a bit of concern from society about the environmental cost of data server and artificial intelligence. They like it. Everybody like it. Sometimes even more, even too much. But I mean, they often do not realize that when you have a kind of service of this type close to your place, you have a huge amount of power, a huge amount of water, and an effect on the climate. And they're now experiencing this point, and so they're requesting some kind of mitigation of this kind of impact on everyday life. So I don't want to say that this is a key point, but it should help motivating the political decision makers to support the beginning of a transition toward thermoelectric thermal management. It's something that is beyond the cost effectiveness, but could be helpful because at the very beginning, you normally need to have some kind of support. This is what happened with photovoltaics and in part also with batteries. Thermoelectrics need to have a support company to start up, because otherwise it's very difficult to start from scratch and competing with the other subjects already on the market.
Thank you, Dario. Umesh, I'm not sure if you have any comment on this part of the applications. You are not from this part of the field, so. But if you have, let me know. But I would like now to open the floor for some questions from the audience, if they exist. I'm not sure if anyone has any questions. If not, I have more. No one? Online? No? Okay. Then let me pick up this point, Geoffrey, where you were mentioning here about the value chain, this problem in the value chain development, where you mentioned this the lack of vertical knowledge, if I so may call, the lack of vertical knowledge for engineering and to develop, let's say, proper functioning thermoelectrics-based technology across the value chain. And my question is mostly for Dario and Emeshe, and is following what we also discussed, or is this something that could be solved by the European Thermoelectric Association and for example, the START Alliance? Will this be part of the work like this? You mentioned also ecosystem building, of course, but is this in line with what you have? Do you have all the actors within these bodies? Will this be in line of what you're doing?
Shall I start? So, like regarding the value chain, what we did in START, we are aware that we are missing the system integrators from the value chain. So that's a key actor we would need to involve better. And coming back a little bit to the previous discussion, also thinking about the actions we planned and which I just presented in the previous presentation sessions, I think we really have to deal with focus on policy making and also the involving of these missing links to the value chain. So if I go back to the policy making, once we have a pilot case, business case, for example, which we have now, of course, it is not yet upscaled, so it's not easy to go with such a result to the market players or the industry who would be producing it at large quantities. But we could still approach policymakers with these and show that this is the evidence, that there is a future for this, and we could use that for promoting these aspects. Thank you.
Well, I see that over these days, and there are a number of ideas about association concerning mostly industry partners, companies, and so forth, which is, from my point of view, very welcome. Of course, as you know, I'm the president of the European Thermoelectric Society, which is open to anyone, and it's not a common society of academicians and pure researchers. We are open to any kind of subject. Of course, historically speaking, we had a majority of people from university in our board, and so this maybe can discourage or demotivate people from companies to from industries to be more involved with the ETS. Everybody is welcome, of course, and this let me take just this occasion to tell you that we have an open call for board candidacies for next September. So if any one of you is interested, is very welcome. He is or she is well welcome to participate in this. But even if you prefer to go for an independent association, my point is let's try to stick together. We are a small community compared to photovoltaics, for batteries, for AI, and so we have to work together toward the decision makers, toward the market, because it's very essential not to dissipate our power. We're very small community needs to be to work together, to cooperate toward a common aim. And in this sense, if the roundtable is named an Industrial Thermoelectric European Association. If you go for a European Thermoelectric Association of companies, that's fine, but let's talk together because we need to have common objectives. Maybe we can move separately, but we have to hit together. Otherwise, we will never succeed in promoting thermoelectricity, which is a common interest of all of us.
May I react on that?
Yes, please, Martin.
So Dario, I think some time ago we sat next to each other in the SustaNet program.
Yeah.
And that initiative was taken out of this program, more or less, or in a combination of initiatives, exactly to bring all these communities together. I think that is, so I fully agree. I'm from profession an industrial guy. I think we need to, when I also compare to other industries that have evolved in the past decades, you see the same move. You start in academic world, and then when it develops, it becomes more industrial, and you have the combination of the two worlds that need to come together. And I've personally seen that happening in the solar industry. I've seen that happening in the battery industry. And I think the attempt that we make here is to do the same here, although the type of applications are a bit more scattered. So that's a challenge. But still, I think the initiative, the cost initiative was done for that reason. And also the STA Alliance is established with the same philosophy later on. So let's see how that goes. But it's not the intention to make a split here.
Absolutely. I'm sure that it is not the aim of anyone. So that's fine.
Yes, this of course, we are not only focusing on Europe, but also internationally. So Doug, you are also welcome to push the US partners towards this type of activities. But I would like to ask you if there is also something similar to this kind of associations or alliances in the US also pushing this type of technology.
Yeah, actually, I am not aware of such in the U.S., and I think it's a great opportunity in Europe. And what I would hope, and I realize that's where it starts in Europe, but I would hope that could be something that could be bridged to the U.S. either through SETS itself or an STA itself, or at least to start a similar type of thing in North America. But really, I think ultimately it would be that those activities, STA or SETS, grows into something beyond Europe and then becomes more encompassing. But yeah, to my knowledge, something like that does not exist in the U.S.
If I can just add a quick thing, it's something that exists instead in Asia. In Asia, it's quite normal that they have this kind of cooperation and among companies and universities and government, and it's one of the strengths of their growth in thermoelectricity. We can learn from them, I think.
Thank you for these comments. Just let me make here a quick rain check. We have, 2 minutes to finish? More or less? 5 minutes. Okay, we started a little bit late, so unfortunately, I think we need to start wrapping up. I have here a final question for you. I have my question here somewhere listed. Now I'm losing papers. Just give me a second. Yeah, so I think we saw through this discussion, if it was not clear for everyone here, but I think we saw that there is potential and there is willingness in the thermoelectrics value and supply chains to keep improving, to find an application, a real application, to find solutions for real world problems, which is in any case why we develop technology, or it should be. But my question here for all of you, and this should be one-liner because we need to finish soon, is what is your number one tip for a successful thermoelectrics value chain? This could be through any part of the value chain. So what do you think is the most important for success. And this question is open for everyone.
Let me start at the end of the pipeline. So as an industrial person, always looking at the end use. We need to reason back from the demand in the market. And I think that's one of the challenges of any starting activity, to have the push buried a bit and replaced by a pull, looking at the market first. And I think that's a challenge for the community.
Yeah, I can follow on. I would say, since we are in Belgium, and we already talked about it, but our national motto is unity is strength. And I really believe that we are a small community and we need to collaborate and share resources to grow thermoelectricity together. And I think if we are just competing against each other, we will not rise thermoelectric, I think.
So my perspective is also similar to what Martin says, that so make people interested in using thermoelectrics, so and find an application which is, let's say, quite popular, and also which is relatively easy to produce thermoelectrics for, and showcase the benefits and make people like thermoelectrics.
I'll jump in. I don't. I sort of had mentioned. I had mentioned cost effectiveness before, and I do think that sort of runs through everything. I think what the START program has worked on with regards to sustainable material that is not scarce, that can be a cost-effective material, is certainly a big part of the of what we need to look at. But I think what's been mentioned in this roundtable is that there's more than that as well. Obviously, as Martin mentioned, in the thermal engineering, there's obviously the manufacturability. There's all the parts that go into making the devices and the subsystems and the systems as well, and all of those parts play a part. So that's sort of my take.
Okay, I'm the last one. I will. If we have to, I should make it in a single word. I would say that the key word is integration. There is no way to make an interesting thermoelectric device, either a peltier or a thermoelectric generator, if you think just about the material and you forget about the structure of the device, the interface, the contacts, the heat exchangers, the way you use it, and so forth. Which means that this kind of integration calls for a very strong interdisciplinarity. And I think this is the charm of thermoelectricity. You don't work on a single part of the problem. You have to see all the parts of the problem. Otherwise, it will get nowhere. So I think that's a key point about making successful thermoelectrics.
Okay, thank you everyone, every participant. I think we have here also a nice outlook for the future, hopefully led by this joint collaboration among institutions, not only the associations but also the universities, the research centers, the industry. So hopefully, I think we can see a light at the end of the tunnel for thermoelectrics after so many years. So once again, thank you everyone for being here, available for this talk. Thank you for the participants. And I believe now we will have some closing remarks on this day from the START coordinator. So I will ask you to please take a seat. The participants who are here to take a seat. Online, if you could stay for these remarks, and another applause for the participants. Thank you very much.
Thank you.
Thank you all, okay, for the very nice talks today and discussions also during this final roundtable event. So here my slide tries to summarize what the different presentations about the START project was about, okay? We have done a lot during these 4 years, and I think we achieved a lot. So this is something that should continue in the future, in the near future. As also what we have listened during the roundtable, there is a strong need for reinforcing coordinated initiatives among the thermoelectrical community. But what I would like to end today with you, besides acknowledging today again for the European Commission for founding the project START. So in every presentations that I've made during this for the START project, related with the START project, I always ended up with an image or a picture of all members of the consortium. That was something that today in the morning I didn't did it today, okay. But that was intentional because I wanted to leave here for the final talk here to end our workshop. So if you remember, during the kickoff meeting, we had a lot of discussions. A lot of us, some of us were aware or didn't understand very well the thermoelectrical technology, and some of the others didn't understand the language of the geologists, for example. And I think today, after this period, at least here on the consortium, we can speak between us and speak almost the same language, which was not the case during the kickoff meeting, I think so. So I want sincerely thank you, all of you, for your dedication and commitment during this period, okay, for achieving the results that we have achieved, okay. I lost a lot of air during this period, but I wanted to conclude here. So we have demonstrated a true European collaboration, and we were able, in fact, to turn ideas into impact. And I hope this will continue in the future, okay? Thank you a lot for you, those who are here physically present, those that have collaborated in the project and they are no longer in the consortium, and also for those that are not there in the picture. Thank you, okay?